Hello friends, today we are going to discuss about stack data structure. So the agenda of this video would be to discuss the definition of the stack data structure. Then we will go through the properties and methods which can be performed on a stack data structure. We will do a programmatic implementation of the stack, and then we will finally analyze the runtime and space complexity of our implementation. So let's start with the definition of the stack. So what is a stack? So stack is a sequential data structure. So it's very important. It's a sequential data structure which works on a principle of last in, first out, or what we call LIFO. So I'll come to these two concepts in a bit. Another constraint or a property of a stack is that it only allows access to the topmost element of the stack. So you cannot access any other element of the stack. The only element which you can access is the topmost element of the stack. So let's take a deeper look into the definition or onto this definition. So first, stack is a sequential data structure. So by sequential data structure, we mean that you cannot randomly access any element of the stack just like that. There's certain order which starts from the start or end of the stack, and then you have, in order to access any other element of the stack, you have to go through all the intermediate elements in order to access that particular element. So that's a sequential data structure. It works on a principle of last in, first out. So what that means is, if you insert certain elements into the stack, the last element which is inserted into the stack is going to be accessed first, and then it only allows access to the topmost element of the stack. So you can only access the topmost element, and in this case topmost element will be the last element which was inserted into the stack. So take an example. Let's say we have certain elements called certain series of number called 2, 4, 8, 13 and 1, right? And we insert this into our stack. So let's say we visualize a stack with this kind of a container, right? The first element we insert into our stack is 2, then we insert 4, then we insert 8, then 13 and then 1. So the last element which was inserted into the stack is 1. That becomes our topmost element, right? So let's look at the property. So stack is a sequential data structure. That means you cannot access any other element in the stack just like that. You have to start with some element from either start or the end, and then you have to traverse through the entire stack or through the intermediate elements in order to reach to a particular element. So if you want to reach, let's say 8, number 8, you have to start from the topmost element. So that's the third property. You can only access the topmost element. So you can start from the topmost element, access 1, then 13, and then only you can reach 8. So it is a sequential data structure, means you have to traverse through intermediate element in order to reach a certain element. It works on the principle of last in, first out. That means the elements which were inserted last has to be accessed first. So in this case, if we want to insert, so elements were inserted in the order of 2, 4, 8, 13 and 1. But when you are accessing it, you can only access 1, then 13, then 8, then 4 and then 2. So if you were to access this element, then the first element you access will be 1, then 13, then 8, then 4 and then finally 2. So this is called LIFO, last in, first out. And the only element which you can access is the topmost element. So if you want to access the element of the stack, you will always access 1. In order to access 13, you have to remove 1 from the stack, and then only you can access the next topmost element, which will be 13 in that case. If you want to access, let's say 4, so you have to remove 13, which will expose 8 on the top, remove 8, and then only you can access 4. So that's the those are the 3 properties or constraints which the stack puts in. So let's take some operations which we can perform on the stack. So as if you can see from this example which I gave, the first operation is push operation. So push operation is inserting an element into the stack. So we have certain container and push inserts that element into the stack. while maintaining the three property which we discussed just now. Then pop removes the element from the stack, and since the third constraint tells that you can only access the topmost element, so pop removes the topmost element from the stack. And then the third operation is peek. Peek just returns the value of the topmost element of the stack without removing it. So if our stack is, if we take the example of our previous stack where the elements were inserted as 2, 4, 8, 13 and then 4. So we pushed these elements into the stack through, so we inserted these elements through push operation. Sorry, this is not 4 but 1. So we pushed the elements into the stack, and peek, if we do a peek operation, currently the stack's top is pointing to 1, so peek will return 1. Now if we pop, if we call pop operation on the stack, it will remove 1 and then the next top will be 13, and if we do a peek, we will get 13 as the value returned. So peek only returns the value of the topmost element without removing it. Pop returns the topmost element from the stack and removes it. So those are the difference between pop and peek. Hopefully this is clear. Let's take some example where this property of a stack can be helpful. So just visualizing how the stack work, we can use it to our advantage when we have to reverse a string. So let's say our string is ABCD and we want to reverse it so that the return string is DCBA. So stack can be very handy. So let's say we have a stack, we insert each character of our string into the array. So in this case we have a string as A, B, C, D. So we pushed each character of the string into the stack, and now we pop them out independently and reconstruct the string. So the first two come out will be B, then C, then B, and then A. So we can easily reverse a string by using a stack data structure. Another property or another example of a stack where a stack can be helpful is to check if a string is palindrome or not. So it's just an extension of the previous example. So if you insert each character of the string into a stack and then pop all the characters and reconstruct the string, if the reconstructed string is same as the original string, then the string is a palindrome. So let's take an example. So let's say our string is A, B, B, C, C, D, or A, B, B, C, C, A. Let's make it a little clear. So A, right? So what will happen if we insert this into, no, sorry, actually this is not a good example. Okay, so let's say our string is ABB, A, right? Now if we insert this string into our stack, we will insert into the stack in the order of A, B, then B, and then finally A, right? Now we are popping them, the characters, and reconstructing the string. So the first to pop out is A, then B, and then A again. So in this case you can see the original string and the reverse. So when we pop a characters of this string into the stack and then we get a reverse of the string. So original string and the reverse of the string are same, that means it is a palindrome. So we can easily test the palindrome property of a string by using stack data structure. Another example is if you want to reverse the words in the string. So let's say our string is he is a lazy boy, and we want to construct the string so that the words are reversed. So in the first example, this whole string was reversed, but in this example, we are reversing the string where the words are reversed. So he is a lazy boy becomes boy lazy is he. So what we can do is we can tokenize our string into each word and insert those words into our stack. So the first word is he, then we have is, then we have then we have lazy, and finally we have boy. So we have tokenized our string, separated string into independent or individual words, and inserted those words into the stack. So the push operation would be he is a lazy boy. And now we are going to pop all the words and reconstruct the string. So the first word to come out will be boy, then lazy, then then is, and then finally he. So we have reversed the individual words in the string. So these are some of the examples, programming questions which are asked in interviews, and you can solve easily with a stack data structure. So now we know what a stack is, what is the definition of the stack, what are the operations we can perform the stack, some examples. Let's do an implementation of the stack and how we can implement a stack in a programming language and implement these three operations.
Alright, so now we are going to implement stack data structure. We will use Python as a programming language. You can follow the same pattern to implement stack in the programming language of your choice like Java, C++ or any other language which you prefer. So to begin with, I'm going to create a class called stack where I will define my constructor which is going to hold the properties my stack is going to use. So the first property which I want to define in my stack is going to be the max size, which is the maximum number of elements my stack is going to hold. I don't want my stack to grow or to hold infinite number of elements, so I want to put some upper bound on my stack. So the max size will be the maximum number of elements my stack is going to hold. So to implement this, I want to define a constant called max stack size, which I am currently set to 50. And I also want to give an option for my client program to provide any value which they want to set the stack to. So in the constructor we can pass a value of size which will be then defining the maximum size. So if size is none, so if there's no value provided in the constructor, I will set max size to the default maximum size which is set to 50. Otherwise I can override and set my max size to what has been provided in the constructor. Okay, now the next property of my stack is going to be the container which will hold the items or the elements of my stack. So I'm calling it items, and it is of type array. So remember, stack is a sequential data structure, and here I'm going to use array to implement my container. So my array is going to be of size defined by the max size, and by default all the elements in my array are set to none. So I define an array of size max size and initialized all the elements to be none. So that is my container. And the next property which I'm going to define is the variable called top, which is going to hold the index of the topmost element or the last element which has been inserted into the stack. So I initialize it with -1 because currently my stack does not hold any item, and as we add more elements into the stack, we will increment the value of the top, or when we pop an item from the stack, we will decrement its value. Alright, so with this constructor, let's define the three methods we identified to implement for our stack data structure, which are push. It pushes an element into the stack. So push or insert an item into the stack, increasing the size of stack by 1. I'll come to the implementation a bit later. let's first define all the methods. Then we will define pop, which is removes and return the last the, or the current top element from the stack. This reduces the size of stack by 1. So we'll implement this method, and then finally we will implement peak operation. So this is similar to pop. The only thing which will not happen here in peak operation is we do not remove anything from the stack. We simply return the current top element from the stack. Number of elements in stack remains same. So there is no change in the number of elements or the size of the stack. So we'll implement this method. Now to implement all these three methods, we will define a couple of helper functions. So the first helper function which we'll define is to check if is stack empty. So returns if our stack is empty. So returns true if our stack is empty. We will implement this helper function, and we will also implement another helper function to get the current size of the stack. So stack size, or we can also call it as a size of stack returns number of elements currently in the stack. So we'll implement these two helper functions. So let's start first with implementing the helper function. So is stack empty? So is stack empty means that there are no elements into our stack. So to implement this, we can make use of the top variable which points to the index of the last element in the stack. So remember, if it is set to -1, that means our stack is empty. So we'll use, so this will return true if self.top is -1, that means our stack is empty. Otherwise it will return false, that means our stack is not empty. And to implement the size of stack, we can again use the same variable top to determine the size of the stack, because top is always pointing to the top of the stack or the topmost element of the stack. So index or rather index of the topmost element of the stack in our array. So the number of elements in the stack will be the value of the top plus 1, because top is is pointing to the index of the topmost element of the stack, and since our implementation of the container is zero based index, so we will just simply to get the number of elements in our stack, we will simply increment by 1 and return the number of elements in our stack. So this will return self dot top plus 1. So if our stack is empty, the top value of the top is -1, and we return -1 plus 1 is 0, so there are 0 element in our stack. If let's say there are 15 elements into our stack, so the top will point to index 14, and we return 14 plus 1 equal to 15 as the number of element or the size of the stack. Now with these two helper functions, let's define the three operations of our stack. So first we will define the push operation. So push operation inserts an item into the stack and increases the size of the stack by 1, right? But before we push anything into our stack, first we need to see if our stack is not overflowing. That means stack is already not holding the maximum number of elements it can hold. So we'll do that check first. So if self dot, so first we will get the size of stack, and if the size of stack is already equal to max size, that means stack is already holding the maximum number of element it can hold, it will raise an exception, stack overflow. Otherwise, what we will do is we will increment the top pointer by 1, because that's going to be the new index at which we are going to assign the incoming element into the stack. So first we increment the value of the top by 1, and in that new index we will assign the new item which we are going to push into the stack. So we simply set the value of the index of the top to be the new item. So we first incremented the top to 1 so that we get the new index where we are going to increment, where we are going to push the new element, and then at that index we assign the new element. So this increments the, this implements the push operation. Now we will implement pop. So pop returns the current top element from the stack and removes it. So first, before we do a pop operation, we need to check the size of our stack, and if the stack is empty, we cannot perform any pop operation, right? So if self.is stack empty, so means if our stack is empty right now, we cannot remove anything, we cannot pop anything out of it, so we raise a value error, stack underflow, right? Otherwise, we store the value of the current top element, so we use a variable called val, and in that variable we assign the element which is stored at the current top, right? So we have stored it into val. Now we will set the current top element to be none, because we also want to remove this item from the stack. Sorry. And since we are removing this element from the stack, we also want to decrement the top pointer to by 1, so that top now points to a new next index of the item which was inserted into our stack. And finally we return this value which we have stored in variable called val. Okay, so this implements pop operation. So all we did was store the current top element, then assign the and then set the item at the current top index to be none, and then decrement the top index by 1 so that it now points to the next top element, next index where the top element will be stored, and then returns the value. Peek operation is going to be similar to pop operation. So first we check if our stack is not empty, because we cannot peek from the stack unless our stack has some elements. So we check that, and then just simply return the, because we are doing peek, it does not remove anything, so we just simply return the value which is stored at the top of the stack. And how we determine that is through our variable called top. So it points to the topmost element in our stack, the index of the topmost element, and we simply return whatever is the value stored in our topmost index. So we have implemented our stack here. Let's see how we can use this stack data structure to solve one of the problems we identified in our previous section of the video. So we will try to see if we can use a stack to reverse all the words in a string. So let's say our string is he is a lazy boy. So we want to reverse the words in our string so that the resulting string is boy lazy is he, and we will see how a stack can be used. So first we take a object of our class stack, and then we tokenize each word of this string. So we are going to split this string into independent words. So my words is going to be an array which holds all the word in other incoming string. So words will be holding he is a lazy boy words. Okay, now each of these words we are going to insert or push it into the stack. So for word in words stack dot push word. So effectively we are inserting he, then is, then a, then lazy, then boy into our stack. Now to test it out, let's do a peek on the stack. So current top element of the stack is stack dot peek. So we're just doing a peek operation. So this print should print the last element which was inserted into the stack. So the elements which we inserted into the stack were he, then is, a, lazy, boy. So the last word which was inserted was boy. So if we perform a peek operation, this statement should print boy as the answer. And then let's reverse this string. So reversed string is an empty, and then we will construct this string by popping elements out of the stack and then appending it into our reverse string. So while not stack is stack empty, so until stack is empty we are gonna pop words from the stack and append it into our reverse string. So reverse string plus is equal to stack dot pop, and then we will just assign a space between individual words, and then finally let's print reversed string is reversed string. So this print statement should print boy lazy is he. So if our implementation is correct, we should get the answer as reverse string where each words are reversed. So let's execute this program. Stack.py. Alright, so you can see my first statement was to check the current last item which we have inserted into our stack, which was boy, because the string was he is a lazy boy. So boy is printed because we are just peeking it, and then we constructed a reverse string which becomes boy lazy is he, which is the reverse of he is the lazy boy. So we have just reversed the independent word in the sentence. So this demonstrates how we can effectively use stack to solve these kind of a problem. If we just want to do quickly analyze the complexity of each of these operations. So first, in terms of a space, we are initializing our stack to be of certain max size. So our stack is going to take an order of n space, where n is the max size which our stack is going to hold. So that's a space complexity. In terms of runtime complexity, since our implementation is through an array, and all we are doing is assigning an item to an appropriate index, so this is a constant time complexity operation. In terms of pop, again we are just simply returning the value which is pointed by the top index, right? So not doing anything, any looping or anything. So we're just returning the value which is stored at the index pointed by top variable, and then just decrementing the value of the top after we have returned it. So this is again a constant time operation, and peak is also a constant time operation. So that's our runtime complexity of the implementation of our stack. So all these three operations are constant time operation. So hope you enjoyed this video, and if you have any comments, please do provide it so that I can take it as a feedback and try to improve it in our next video. Till then, happy programming. Goodbye.